So our most recent topics have been this idea of what are called line integrals. And these are integrals. There's two types we studied. The first was we integrated over a curve C, and it was of some scalar function, f ds. So here, f is what we call scalar valued. So it's R2, or let's just do the arc3 case just to kill all the stones, or kill all the birds with the same stone. So this is what's called scalar functions. And then the second type is we're integrating over some curve of a vector field. And so the correct way of doing that is like this. And so here, f is a vector, and in the most general setting, it takes a vector, or it takes 3 inputs, and it spits out 3 inputs. So this notation is a little more advanced, but you kind of got to gain with it. There's a lot of context that you need to understand. So one of the things that I know was curious to me when I was a student is I would say, why do you call them line integrals? Because you're really, this thing C, it could be a line, but in general, C is just some curve, right? So in many ways, maybe a more proper term would be these are called curve integrals or something, but that's just not what they're called. They're called line integrals. What we found in our examples, and what we'll find when you guys, well, what you'll find when you work on the homework problems and do some practice, is that in many cases, these are complicated to compute. I mean, so we also recognize that the definition of these creatures is a scary Riemann sum. And even if we don't appeal to the definition, then the theorem that tells us how to integrate them involves the parametrization of C. And that can often be ugly. So long story short, these are, in general, somewhat complicated to compute. So in general, these are tedious to compute. Even when we can reduce them to an integral we studied in Calc 1 or Calc 2, they're often tedious. And so the question we're going to ask is there a better way? And what we do when we're always looking for a better way, we think about the simplest type of case. And so the simplest line integral is one where you're not integrating over a curve, but you're integrating over a line, in particular, an interval from, say, A to B. So if you integrate a function over the line from, on the x-axis from the point x equals A to x equals B, that's just a traditional integral, and you could see that for yourself. And one of the nice things about a traditional integral is we have what's called the fundamental theorem of calculus. And the fundamental theorem of calculus gave us a very shortcut. I shouldn't say a very shortcut, that doesn't make any sense. It oftentimes gave us a shortcut for computing integrals. And it also makes a very special connection. It connects a derivative with an integral. So here's a question you might have. And if you don't have it, maybe by me writing it down, you'll say, oh, this is a good question. So the fundamental theorem of calculus says the following. It says this traditional integral. Now, I'm going to write this a little different than we wrote it in Calc 1 or Calc 2. Remember, how did you evaluate integrals? You said if I'm integrating f, and I know an antiderivative, so we would write it like this. We would say that this equals g of b minus g of a, where g is any antiderivative of f. So what another way of writing that is that just means g prime equals f. So that's how we learned to integrate functions way back in Calc 1. You use that. You leaving, Ricky? Hold on, we got to say goodbye to the demons here. Ricky, not demon. Oh, I meant demon. I'm sorry, I forgot. Not you. Ricky, come say bye. Bye, Ricky. Have fun. Okay. Listen to mommy. Okay, so again, this is what you did when you wanted to integrate x squared. What's the antiderivative? It was x cubed over 3. So the beautiful thing about this formula is that A, it is relating a property about the whole function f just by looking at the value of its antiderivative at the endpoints of the interval. So again, you are integrating over AB. So it turns out the only thing that matters, what's really, see you guys. Bye. It's like they don't care. Anyhow, working from home, so fun. Draw a picture of this. And actually, before we draw a picture of it, let's rewrite it. We could rewrite this in a more sophisticated way. Instead of writing some new function g, we can write it like this. So we can rewrite the integral from a to b of any derivative. So let's say f prime of x dx is equal to f of b minus f of a. So think about that for a second. Ponder it. This says the same thing as the previous page, only we're not using two different letters. We're writing it as this is more mathematically mature. I mean, check it. Pick a function f, and then check that this checks out. So the cool fact is the following. This thing right here, the actual integral depends only on the boundary, whatever that means, but we'll make the boundary of the interval. So if we're going to say that there's a boundary to a comma b, what would it be? It'd be the endpoints, right? The endpoints. There may be questions about this. Think about it this way. We're integrating over the interval a, b. So the set we're integrating over is an interval. And what's fascinating about this, the fundamental theorem of calculus, is it tells us that what's happening in between a and b really don't have any effect. Really, the area under the derivative is nothing more than the net change of the function, f of b minus f of a. So let me give you a quick, let's just look at a very obvious example just so you understand this formula is not some gibberish. So let's integrate, suppose f of x is 1/3 x cubed. Then what's f prime? F prime is just x squared, right? And so clearly the integral from, say, 1 to 3 of x squared is just, as you guys know from calculus, 1/3 x cubed evaluated from 1 to 3, which is 27/3 minus 1/3, which is, of course, 26. So you might want to compare that specific example in blue with the general statement above it. Ponder it. Okay, so if you go to the previous slide, I said question. Here's the fundamental theorem, this what it says. And so the question we might ask, is there an analog to this for line integrals? I mean, that's a perfectly rational expression, or excuse me, question. Is there some analogy where we're integrating something over a curve, and we want to ask ourselves, is it possible for, say, f dot t ds to be equal to number minus number? That's essentially what we're asking, right? Or f ds equals number minus number. So what do I mean when I say f ds equals number minus number? We'll go to the previous page. If you look at this, the beauty of the fundamental theorem of calculus is it takes a very difficult computation and essentially says it's arithmetic. It's you plug a number into two expressions, you plug two different numbers into the same expression and subtract. F of b is a number, f of a is a number, number minus number. But if you think about it, it's quite a powerful thing. If you went back in your calculus 1 notes and looked at this thing in blue and said, okay, I'm going to show this integral 1 to 3 x squared. Oh, by the way, I should have a slight misstep here. If I'm being a little nitpicky, should have a dx there. But if you went back and tried to compute that integral from the definition, it's very complicated. There's limits and all kinds of ugliness. This is very simple. And so the question is, can we do this for line integrals? And of course, I wouldn't be posing the question if it's not going to be true in some sense. So our only goal is to figure out when. So the answer, yes, but in a certain sense. So that's kind of what we want to talk about. Anybody have a question? Okay, so to do this properly, we need some technical terms. So we don't want to get too bogged down with all these terms, but we do need to have a notion of what they mean. Basically, we're only going to be interested in certain types of curves. Other types of curves that have, quote unquote, what we might say bad behavior, we don't want to consider them, because things don't always work out when the behavior is bad. So here's some things we want to talk about. So a curve is called simple. So this is a name we're going to give to something. So we have to understand what the word simple means. And there's some technical terms for these things maybe you've heard of before, like things like one-to-one and stuff like that. But a curve is called simple if we evaluate it at one point and we evaluate it at any other point and they never equal to each other. Now, there's lots of context happening here. Clearly, I'm telling you a curve has a parametrization R. And what this means in English, not in math terms, it means the following. This just means the curve doesn't intersect itself. So let's just draw a picture of what that might mean. So remember, every curve that we parametrize, we are giving it a direction. So this guy right here is simple. Now let's draw one that wouldn't be simple. This guy would not be simple. If I drew that wrong. Why would this guy not be simple? It would not be simple because it intersects itself. And this particular one intersects twice. So when we say this, when I write over here RT1 does not equal RT2, this point right here, which I'll denote red, that point right there that we'll say this is R of T sometime equals R at some other time. Does anybody have a question about this? Okay, so it's a very, if you don't want to look at the scary math, that's great. You don't have to. Just think simple means it doesn't intersect itself. All right, so that's the first term we need. Next, we need closed. Closed means exactly what you would think. Closed means that R of A equals R of B. So what does that mean? That could mean anything like this. This guy is not closed. Does anybody have a question about that? We can draw some other guys. Let's just, for fun, we could say This guy right here is not just closed, it's simple. This is not closed and simple, right? Because it doesn't intersect itself. But then down here, I could draw something like this. This guy is closed and not simple. Does that make sense? Maybe. It turns out when we do these integrals we're going to start doing today, well, even line integrals, knowing when a curve is closed and when it's simple is going to have very important consequences. And what I mean consequences, I'm talking particularly about making things easier or complicated to evaluate. Okay. All right, so our next guy, this is a little more advanced now. A region in R2. So now we're talking about not a curve necessarily, but a region. Is said to be connected. If it is open and any 2 points can be connected by a curve, and it has to be continuous in that region. So as you would imagine, you can think of this in a very colloquial English sense, what we mean by connected. Something's connected is if you pick any 2 points in it and you can draw a curve to them. So let's draw a picture here. This is a region. This guy is connected. Even if it has a hole in it, this guy is connected. So what am I talking about? What region? Well, this would be my region here. Let's shade it in just so we understand. Of course, this would be the whole thing. So again, if you look at these 2 regions, pick any 2 points, you can always draw a curve from one point to the next. So, you know, here's a point, here's a point. I can draw a curve to it. Over here, I can still draw a curve. In fact, you could think of many curves you can draw from point to point. Right? Now, that clearly tells us, or at least gives us an idea of what not connected would mean. And you can imagine this without even all these fancy definitions. Not connected would be something like this. If it is not connected. Because if I pick a point here and here, there's no way I can connect them because it wouldn't be in. There's no way I can connect these 2 points. Does anybody have a question about this? Now, why am I going over this? Because we're going to state some theorems coming up, and all these theorems rely on these terms. And it's a weird position for me to be in because, to be fair, in Calculus 3, we're just learning the basics of all these things. I've said this before. So part of me says, why waste time with these fancy terms? They don't really have any connection in this class. I mean, I could easily have taught what I'm going to teach later without mentioning all these, but it is nice to give you a little bit of feel for these terms. So, you know, I'm going to go with it. Okay, we have 2 more definitions. Whew. So, a region is simply connected. So now we're going to add an adjective to connected if the following. First off, it's open and every simple closed curve can be contracted. To a point. So this is a very fancy way of saying it has no holes. So if we draw those examples we had before, this is a stronger type of connected. This guy right here is simply connected, no holes. This guy is not. Why is it not? Because there's a hole here. And if I take any curve around this hole and I try to contract it to a point, it will be stopped because of the hole. But that would not happen over here. Take any curve, I could shrink it down to a point. So this, again, this is a little sophisticated, and we're sort of asking you to have some you know, leeway with the technicalities, but the idea is simply connected. One way you could think about it is there's no holes. Okay, does anybody have a question about this? So again, this is some terminology. All right, so our last definition is one that's a little more calculus based and not geometric at heart. So we say a vector field F is conservative if it votes for Republicans. No, is conservative if there is a scalar function phi with F is actually the gradient of phi. So why are we defining this? Well, remember what our original thought process was today. Our thought process originally was, how do we generalize the fundamental theorem of calculus? Does anybody have a question? Okay, so what's special about these creatures? Obviously, if we're defining all this crap, there's got to be a reason. What's special about them? Well, what's special about them is the following. Let's just do some math. We haven't done math yet. We talked a lot. We haven't really done anything. So assume C is any curve with parametrization, or let's, instead of writing all the words, let's just give you the so I guess I don't know. Perhaps I should say, I'm trying to think of the best way to write this. I mean, I think that I've been sort of, maybe the context is helpful, but anytime I'm talking about a curve C, I hope you realize, I've said this before, but it's worth repeating. I can take a curve C and I can parametrize it in more than one way. So you have to keep that in mind. We talked about that briefly in Calc 2. We've talked about it a few times now. But more importantly, anytime I say C is a curve, I want you to think automatically that what we're dealing with is C has some parametrization. And let me be very, very specific. We need to, if any of this is going to work, we have to describe C using some parametric equation, or if you'd like, some vector equation. So C is R of t, and it has an x component depending on t, a y component depending on t, and a z component that depends on t. And then we have to have a domain for our curve, or where does t range? Well, typically, unless otherwise stated, we say t starts at some value a and ends at some value b. So the next thing we want to assume is that f is conservative. It is equal to the gradient of some scalar function. Now we have to be very, very careful here. F takes on an input of x, y, z. It spits out 3 components. Each one of those components can take on x, comma, y, comma, z. So let's remind ourselves in detail of what this means. This means f, which has an input of x, y, z, is equal to the partial of phi with respect to x at x, y, z, the partial of phi with respect to y evaluated at x, y, z, and then the partial of phi with respect to z evaluated at x, y, z. So that's really what this creature looks like. Okay, so let's compute. Let's see what happens. So I'm going to write this a little different. I'm going to write the line integral of c as the gradient of phi dot dr. So we talked about this for a second. So this is just f dot dr. That's one of the ways that we can write a line integral. We talked about this on Monday. Another way of writing this is the integral over c of the gradient of gradient of phi dot t dot ds. So this is nothing more than, this is the definition. But I'm not using f, I'm using f equal to the gradient of phi. Okay, so let's plug in what all these creatures are. This is the gradient of phi. What is t? Well, t we know is r prime of t over the length of r prime of t. And what is ds? We've done this a few times. That's r prime of t length dt. And we know these guys cancel. So this now equals the gradient of phi dot the derivative of r dt. Okay. What is this inside equal to? Well, let's write it out. Let's write out what the inside is equal to, because it looks like it's compact, but does it give us anything? Oh, by the way, don't forget, I got to come back here. I made a slight error. Once we do this, remember, now we are not integrating. These two integrals now, once we go from ds to dt. Remember, once we go from ds to dt, this is now a traditional integral. So this is a to b. This is a to b. So what is happening here? Well, let's write it out in all its glory. What is the gradient of phi? Well, I'm gonna use shorthand. This is phi sub x, phi sub y, phi sub z. And then this is dot. What is r prime? Well, we know what this is. This is, we can write it either x prime. We can write it as dx dt. Or, you know, let's use primes. It's a little cleaner. I can write this as x prime of t, comma, y prime of t, comma, z prime of t. And then that's dt. So let's move this comma. It's kind of causing us a headache. So all I'm doing now is writing out what each of these derivatives actually looks like. So one of the things that's difficult when you're first learning this is, you know, when I write this dot, is it a dot product? Is it traditional multiplication? It's hard when you're a beginner to always keep in mind, what is this a scalar? Is it a vector? How am I doing this manipulation? Remember, the gradient is always a vector. And particularly, I have this creature right here, this r with an arrow, just to remind you that r is a vector. So now we want to take the dot product. We want to take this times this plus the second coordinates times each other and add them together. And then the third coordinate, we're doing the standard dot product. So this becomes the integral from a to b. So you have phi sub x times x prime of t plus phi sub y, this partial, these are partial derivatives, don't forget, times y prime of t. And then lastly, you get the partial with respect to z times z prime of t, which to most people who are taking this class for the first time, or maybe even if you've done lots of math, you might not recognize what we have here. But what we have here is a very, very simple creature. Because if you truly understand the chain rule, what you'll recognize is this is nothing more inside here is nothing more than the derivative of phi with respect to t. Now, this is a big leap for most people. I know it was for me. This is the chain rule. So think about why the chain rule applies here. Phi, what is phi? Phi is a function of what? Well, remember, phi is some scalar function. It takes on x, y, and z, and it spits out a number. But don't forget that x is also a function of t. That y is also a function of t. That z is also a function of t. So by the chain rule, you take the derivative of the outside. What's the derivative of phi? It's the gradient of phi. Evaluated at the inside, which is x, y, z, times the derivative of the inside. So once again, this is a big leap for most of us, especially notation-wise. What I would highly encourage that you do is I would highly encourage that you try to think, well, it's not easy to get this. I'm not going to pretend it is. But I would encourage you to try. So let's kind of remember what the chain rule says. So for those of you who are interested in getting to the bottom of this, don't forget, what is phi? Phi is a function from R3 into R. R is a function from R into R3. Scariness. So what is phi evaluated at R of t? Because that's really what we're doing up here. Phi evaluated at that. Well, what does R do? R takes on a number, associates it with three numbers, and then phi takes those three numbers and associates it back with a new number. So what is the derivative of this with respect to t? Well, the chain rule says you differentiate the outside. So you take the derivative of phi. Well, that's a gradient. The derivative of phi evaluated at the inside times the derivative of the inside. That's the chain rule written in Calc 3 language because we have multiple variables. That is the chain rule. Not easy for us to understand the first few times we see it. I get that. I have the luxury of have been doing this stuff for 20 years. You have not that luxury. So it's very hard if you just aspire to make sense of this to get to the bottom of that. And again, I can't emphasize this enough, and I'm not pretending this is easy. This is a dot product. This is a vector. This is a vector. Woo, that's a lot. Now, all this scary stuff is scary for a reason. It's a proof of a general thing. And so we can now state that, and we actually just proved what we set out to figure out beforehand. And that is an analogy of the fundamental theorem. So let's write it down. Oh, by the way, if you don't see it, let me just finish this. Let me go back to the previous page. Because maybe I shouldn't assume you saw it. If you look at this last line, I shouldn't have put a period here. We're not done yet. We have one more line to go. But this is nothing more than the one-dimensional fundamental theorem of calculus. So this is by the thing we wrote at the beginning of class, phi of b minus phi of a. So the last line is the fundamental theorem of calculus. Because I have a derivative inside of that integral. And the fundamental theorem tells me that if I know the antiderivative, I get phi of b minus phi of a. All right. So let's write this down, and because we want to show you how to use it. So basically, the fundamental theorem says this. This is exactly what we were hoping to get. So if let me write it. I don't want to write it that way. So if f is conservative, if it equals the gradient of some scalar function, then the line integral of f dot t ds, which is, we could write it as FDR, but it's okay, we're not going to. This equals phi evaluated at r of b minus phi evaluated at r of a for any c let's be very specific. Let's just write the generic thing where C makes sense. So again, I don't want to get into technical details of open sets, and basically we need phi to be differentiable. By the way, if I go back here, I guess I should be a little more careful. This should really yeah, okay, let me be a little more careful here. I don't want to speak this might be this might be, the context might be off. Let me be very careful here. Phi doesn't make sense at A and B, so I'm kind of abusing notation. I don't want to do that. This is really R evaluated at B, and then phi evaluated at R evaluated at A. So actually, what I mean is what you see right here. This is what we actually proved. Now, the good news with this is if you know the vector field's conservative, you have a simple way of doing it. The bad news is, if you don't know it's conservative, is there a simple way? And not only that, this only works if you know this function phi. If you don't know the function phi, then there's not much you can do unless you know how to find it, which we'll talk about next. So let's make note of that. Here's the good news. The above theorem can make difficult calculations simple. But of course, the bad news is can only be used when we know f and phi. If I just give you some vector field, there's nothing that says what phi should be. Now, of course, we can create examples easily by saying, here's f and here's its corresponding phi. But in general, in practice, in the real world, there's nothing that says how to do that. Well, I shouldn't say there's nothing that says we're going to show you a way to do it, but there's nothing that says it's obvious. So that sets up the next question. Given f, can we compute phi? Right? Because that theorem is only useful if we have a vector field f and then we know what phi is. That's the only time it's useful to us. Just like the only time the fundamental theorem of calculus was useful to us in Calculus 1 and in Calculus 2 is if we knew the antiderivative. So now I worded this question because I'm being sort of a jerk. Well, maybe I'm a joke too. I don't know. Turns out, not every f is conservative. But when it is, we can compute phi, theoretically. Not saying it's easy. So that's what we'll do next time. So does anybody have a question? Comment? Concern? All right, well then work on those line integrals. Try not to use this cheating method right away. Even though some of the ones on the homework, you'll be able to use the cheating method, I think, if you're creative enough, but try not to do that. Suffer through the calculations, check them with technology if you can, and then come back. Does anybody have a question? All right, I'm gonna stop recording.